Hi all, this is lecture 18 on section 5.2 and 5.3 exponential functions. So in the past, we have worked quite a bit with polynomials. And polynomials are where you have an x raised to a number, x squared, x cubed. And now we're going to flip, flip that and talk about exponential functions, which is where your base, the bottom number, is a number this time instead of an x. And your variable, your x, is actually in the exponent. So for an exponential function is a function f defined by f of x equals a to the x for some a greater than 0. Okay. So we get a is a number, any number you want, as long as it's positive and not 0, and x is your variable. Okay. And here are two things that are true for that. So if then two numbers, if you have two x1 and x2 are different numbers, then if you raise them as powers, then the whole thing is not going to be the same either, right? So if you have two things like a 2 and a 3, and you raise them to the power of a 4, then if 2 is not the same as 3, then 4 to the 2 is not going to be the same as 3 to the 2, right? Or actually, they want it the other way. 4 to the 2 would not be the same as 4 to the 3, right? And we know that because 16 and 64 are not the same number, okay? So, but if you go the other way around, so if you have 4 squared equals 4 to the x, then what happens is these two things, these two exponents, must be equal. Okay, it's the only way that can happen. All right, so let's look at a couple of these types of functions. So first of all, let's look at y equals 2 to the x. So when we're going to graph this, we're going to do our table of values. My favorite numbers are 0, 1, 2, -1, and -2. When you plug in 0, 2 to the 0 is just 1, right? Any number raised to the 0 power is going to be 1. Next, we're going to take 2 to the first, and that's just 2. And we're going to take 2 to the second, and that would be 4. Then it gets interesting here when we take 2 to the -1. A negative exponent means it's in the wrong part of the fraction, so I'm going to move it to the bottom. So 1 over 2, or 0.5. And the same thing when we do y equals -2. So 2 to the -2 is 1 over 2 squared, right? I move it to the bottom, make it positive. And that's going to give me 1 over 4, which is 0.25. And if we quickly sketch what this looks like on a graph, at 0, our value is 1. At 1, our value is 2. At 2, our value is 4. As we go to the left, at -1, we're at a half, and then a quarter for -2. And so we kind of get this little swoop that comes through. As we go to the right, it goes up, and it goes up pretty quickly. It's going to go increase to infinity pretty quickly. On the left, it's going to go right along that x-axis. It's never going to touch it, so it never touches the y equals 0. So it's never equal to 0. And it's never negative. Notice that it never goes below. Okay, so we never get negative numbers or 0. If we look at y equals 3 to the x, we can see that again. So a quick sketch here, our table of values, 0, 1, 2, -1, -2. Now you're plugging into the 3 to the x. So when you plug in your 0, again, you get 1. For 3 to the first, we get 3. For 3 squared, we get 9. For 3 to the -1, we get 1 over 3, which is going to be 0.33, or 0.3 repeating. And for -2, you get 1 over 3 squared, which is 1 over 9. And that's going to be 0.1 repeating, so 0.11. And if we take a second and graph that, now notice when I set up my graph, I don't go down because we're not going to go down. And at 0, we're at 1. At 1, we're at 3. At 2, we're at 9. At -1, we're down to 1/3 and very close to 0 as we get to -2. Okay, so you can see that they're very much the same shape. One goes quicker, like the higher your a value, the quicker it's going to go up to infinity. The smaller your a value, the slower it's going to go. Okay. Then let's see what happens if I make it that a less than 1. So keep in mind this is an a less than 1. So if we take our values, 0, 1, 2, -1, -2. Again, when you plug in 0, anything to the 0 power is 1, so that's not going to change. When you have 1/2 to the 1, that's just 1/2, so 0.5. When we have 1/2 squared, that's 1/2 times 1/2, which is 1/4, so 0.25. 1/2 to the -1. Now, -1 usually means move to the other part of the fraction, but when I have a fraction, that means I'm going to flip it over, take the reciprocal. So that's going to become 2/1, which is just 2. When we take 1/2 to the -2, we're going to flip it over and square it, and that's going to give us 4. And if we graph these, at 0, we're at 1. At 1, we're at 0.5. And at 2, we're at 0.25. At -1, we're at 2. And at -2, we're at 4. So now we get the same shape, although instead of increasing from left to right, it's kind of flipped around. And so we actually decrease. Okay, and that's what's going to happen when your a is less than 1. Okay, it also happens if your exponent is negative, because it's kind of the same thing. Okay. A couple of things to note here. Exponential functions go to infinity. They get big really, really fast. So even as long as a is greater than 1, it's going to grow at a faster rate than a polynomial, okay? So if I take an a value that's even slightly larger than 1, like 1 point, lots of zeros and a 1, that's still going to become larger at some point than x to the 1 billion, right? So taking exponentials, it goes much, much faster. Than polynomials. Okay. Now, why do we care about these? One, they model a lot of things. So appreciating value, like if you invest money, okay, like in a bank account, bacteria and cell growth, spreading of diseases, chemical decay, and cooling are all exponentially modeled. Okay, they're interesting. Solve for x and the exponent can be difficult or impossible. So the mathematics of how we solve and work with these can be a little more interesting than just add 2, divide by 5 kind of thing. Okay. Now, some applications here that we want to be careful. We want to make sure that we mention compound interest. Okay, the P here in your formula is your principal. Then principal is the initial amount. R is your annual interest rate expressed as a decimal. So anytime you see an R as a whole number, you're going to divide that by 100 to get the decimal version. N is the number of interest periods for a year. So if you're compounding monthly, then how many times will you do that in a year? You'll do that 12 times. So your N would be 12. If you do it quarterly, that means that you're going to compound the interest 4 times a year. So your N would be 4. T is the number of years that you're investing, and A is the amount that you're making after that time. Okay, so A is your resulting number. Something that comes up very much in calculus is the number E. Now, if you think about the fact that if you take out the R, if you let the R equal 1 and you let the T equal 1, then what you have is this number here. So 1 plus 1 over n to the nth power. And if you let that n get really, 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 really big, right? So n is the number of times that you compound your interest, right? So if we do it once a year, n would be 1. If you do it every 6 months, n would be 2. If you go to quarterly, that's 4. Monthly would be 12. Bi-weekly, so every 2 weeks, would be 26. Weekly would be 52. Daily would be 365. Hourly, you could multiply that by 24, right? And so you can make them really, really big. And if I want to do it all the time, like not just like every minute, every second, then what we do is we say, let's let that number of times that we compound it go all the way to the infinity and get really, really big. And when you do that, what happens is this becomes the number e, and that number is 2.718. Okay, it actually goes on forever, but we're going to cut it off there. Okay. And that means if we let that be the base of our exponential function, then we get what's called the natural exponential function. And this is primarily what we use in calculus, is the natural exponential function, e to the x. Okay, so if we graph e to the x, x and y, 0, 1, 2, negative 1, negative 2 to graph our function. Plug in your 0. E to the 0 is always 1 because anything to the 0 is 1. Then we plug in 1. So e to the 1 is your e, which is 2.72. I'm going to round to 2 decimal places. If we plug in 2, that's e squared. If we plug in e squared on your calculator, we get 7.39.
Thank you.
From there, we're going to plug in our negative 1. Thanks. E to the negative 1 is 1 over e. So if you divide by the 2.72, you get 0.37. If you plug in negative 2, then you get 1 over e squared. And that's going to be 0.14. So we have 2.72, 7.39, 0.37, and 0.14. And if we graph that, at 0, 1, we have a point. At 1 and 2.72, so maybe here. At 2, we're at 7.39, so up here. Negative 1, we're below 1. And at negative 2, we're pretty close to 0. So we get this curve right here. Okay, so very similar to what we saw up above. Okay, particularly because the e is between 2 and 3. So it should look very similar to our 2 to the x and our 3 to the x. Okay. And so if we want to use that idea of continuously compounded, we can. And what happens is we end up that middle piece where we had the 1 plus r over n becomes the e. And so we get this formula for continuously compounded interest where a is equal to p e to the rt. Where again, p is our principal. R is your annual interest rate. So there R is going to be given as a percentage, and you've got to divide it by 100 to get your decimal. T is your number of years, and then A is how much money you have. Okay. All right, and that is the end of our lecture for today.